Hello everyone and welcome back to another video. Today we're going to talk about the AN1 factors and whole numbers outcome. Some of the things that we'll discuss in this video are prime factors, greatest common factors, least common multiples, along with square roots, cube roots, perfect squares, and perfect cubes. So before we move on, let's go ahead and review what a factor is. So a factor is really just any numbers that we can multiply together to get another number. So an example that we have here, we have 1 times 8 and 2 times 4 both give us 8. So we would consider the factors of 8 as being 1, 2, 4, and 8. Another example we could have is perhaps the number 12. We know that 1 times 12, 2 times 6, and 3 times 4 all give us 12. So that means that your factors of 12 are going to be 1, 2, 3, 4, 6, and 12. We should take note that there are also negative factors as well, such as -1 and -8, but we're going to focus on the positive factors in this outcome. So combining the idea of what a factor is, we're going to put it together with our knowledge of prime numbers. So remember from previous courses that a prime number is a number where they only have two factors, one in itself. So we could take a look at some examples such as 2, 3, 5, and 7. Those are all prime numbers because you can only multiply 1 times 2 to get 2. You can only multiply 1 times 3 to get 3, and so on. On the other hand, we can also say that we can only divide 5 by 1 or by 5. Same thing with 7. We can only divide 7 by 1 or 7 by 7. You might remember that the opposite of a prime number is what we would call a composite number. So a composite number just has more than two factors. So any numbers where there's more than two factors, such as 8, 12, 20, and so on. An important thing to keep in mind is understanding why the number 1 is not a prime number. So let's go back to the definition. We know that prime numbers are numbers that only have two factors, 1 in itself. When we think about the number 1, we only have one unique factor. The only possibility to get 1 is just 1 times 1. And since 1 is my only factor, we only have one factor. So therefore, this is not prime. Another situation to keep in mind is understanding why 0 is not prime. So 0 isn't prime because of two main reasons. 0 cannot be divided by itself. And a second reason, we could also state that 0 has an infinite number of factors. So if that's a little bit confusing, think about what you can multiply together to get 0. I can go 0 times 1, 0 times 10, 0 times 1,243, and these would all equal to 0. So since we have an infinite number of factors, 0 also can't be a prime number. So the newest concept here in grade 10 is understanding what prime factorization would be. Since we know that factors are all the numbers that we can multiply together to get a different number, and we just talked about prime numbers, prime factorization just means that we are in the process of breaking a number down into factors that all happen to be prime numbers. So we can look at the number 12 as an example. We can say that the prime factorization of 12 would be 2 times 2 times 3. Or if we look at the number 72, we can prime factorize it as 2 times 2 times 2 times 3 times 3. Note that all the numbers in each of these lists are all prime numbers. So you might be wondering, how do we prime factorize a number? Or maybe even the ones that are a little bit bigger, how do we do that? We can use something called a factor tree. So these are really just trees that are composed of the factors that make up each number in the branch above it. So we can see here in this example that we start off with the number 60 and we split it off into two branches. Notice that 6 times 10 would give us 60, And in the branches below each of these numbers, we know that 2 times 3 gives us 6, and 5 times 2 gives us 10. So as a result, we can state that 60 can be prime factorized as 2 times 2 times 3 times 5, or if we want to simplify the 2's here, we can say that it's 2 squared times 3 times 5. Note that this portion right here that we just did, we would call this a prime factorization. So if your teacher asks you, what is the prime factorization of a number? Remember that this portion right here, this is just a factor tree, whereas the prime factorization itself states what the prime factors of the number are going to be. Note that it's very important to ensure that you have the multiplication symbols here. I know some students tend to write something like this, 2, 2, 3, 5. Having the prime factors listed like this actually is not a prime factorization because it doesn't show that these factors multiplied together gives us 60. So please try to avoid doing this. So you might be wondering, what would happen if we didn't start with 6 and 10? Well, let's try it out. We know that 60 can also be broken down into 2 times 30. The 2 can't go any further, so I'm going to go ahead and draw a circle around it. 30 can be broken up into 5 times 6. 5 is a prime number, so I'll go ahead and circle that. And I can break down the 6 into 2 and 3. And 2 and 3 are both prime numbers, so I'm going to go ahead and circle those. So we can see here I'm left with 2 times 2 times 3 times 5. Oh, well, maybe we fluked out and ended up getting the same thing, so let's try it one more time. So I'm going to say that 60 is the same thing as 3 times 20. 3 is a prime number, so I'll go ahead and circle that. I can break down 20 into 2 and 10. 2 is a prime number. And then finally we have 2 and 5. And both of those are prime numbers. So once again, even though we started with different numbers in our first layer, we end up with exactly the same prime factorization. So we can tell that it doesn't really matter what two numbers we start off with, we're always going to end up with the exact same prime factorization. So moving on to our next topic, let's discuss the greatest common factor, otherwise known as the GCF. The GCF of two or more numbers can be defined as the largest factor that can be used to divide evenly into each of those two numbers. So for example, we have the GCF of 18 and 24 being 6, because it's going to be the largest number that can divide both 18 and 24 without any remainders. So really we're looking for whole numbers. We can verify this and double check our answer by listing the factors of each number and then seeing which factor is going to be the largest one. So we know that 1 times 18 gives me 18, 2 times 9, 3 times 6. So I have 6 factors here for 18. I can do the same here for 24, 1 times 24, 2 times 12, 3 times 8, and 4 times 6. Since we're looking for the greatest common factors, so common meaning the same, and greatest, well, we can tell here that the greatest common factor, or the factor that's the largest and is the same in both lists, is going to be 6. So our GCF in this case is going to be 6. Let's go ahead and try out a couple of different examples of finding out the GCF. Now, a quick tip here, if you are very proficient at mental math, you might find this a little bit quicker to do. You might not need to write out all the different factors or write out the factor lists of each number. You might just be able to figure out what's going to be the largest divisor of each of these pairs and go from there. But let's go ahead and use our factor lists to figure out the GCF of each of these. For the next two here, let's use a little bit of mental math. I know that 18 and 45, the largest number that can divide evenly into both of these, is going to be the number 9. So my GCF in this case is going to be 9. I can do the same thing here with this third example. I can divide both 48 and 120 by 24. So in this case, my GCF is going to be 24. You can go ahead and verify example number 2 and 3 by making a factor list as we have done here. And you can see that we have the exact same answers. So switching gears here a little bit, let's talk about the least common multiple, otherwise known as the least common multiple or lowest common multiple. So this is defined as the smallest multiple that is the same for each number. So if we look at our example of 8 and 12, our LCM is going to be 24. What we can do is we can make another multiples list here, and we have the numbers 8, 16, 24, 32, and 40. Well, how did we get these numbers? Well, when we think of multiples, we are simply adding the exact same numbers. So we can tell here that 8 plus 8 gives us 16, 16 plus 8 gives us 24, 24 plus 8 gives us 32, and so on. Another way of looking at this is thinking of the first number as being 8 times 1, second one is 8 times 2, 8 times 3, and so on. We can do the same thing here with the number 12. So we've got 12, 24, 36, 48, and so on. We can see here that our lowest common multiple or least common multiple is indeed 24. Some of you might be wondering, well, what would happen if I continued on and I ended up getting 48 here? We can see that 48 and 48 are also common multiples, but is it our lowest or least common? No, in this case, it's just a common multiple. So this doesn't really have any significance for us. So the idea of least common multiples is super important to understand when we add or subtract fractions, because when we do so, we're going to have to look for that LCM. So let's go ahead and work through a few different examples. So our multiples of 24 are going to be 24, 48, 72, 96, 120, 144, and I think that should be about enough. Let's do the same with 60. So we've got 60, 120, 180, and so on. And we can quickly see that our LCM of 24 and 60 is going to be 120. So moving on to the next two examples, you guys can try these out and pause the video and then unpause once you've tried them out. So moving on to your next two examples here, you can pause the video, try them out on your own, and then unpause to check your work. So something that I'm sure a lot of you guys have already noticed by now is that it takes a lot of work to brute force the LCM and the GCF, or if you're not too confident with your mental math, it might become a little bit more difficult once these numbers become a little bit bigger. So there's a method called the cake method, the upside down cake method, or the ladder method that we can use to help us find both the GCF and the LCM of two or more numbers at the exact same time. So the idea behind this is we are going to always start with the two numbers on top. So in our example here, we're starting off with 36 and 120. We're going to choose the number that we want to divide by, and we're going to write it on the outside. You can see that when we've chosen the number 2 here, we're dividing 36 by 2 to give us 18. 120 divided by 2 gives us 60, and then we're going to continue on. We can see that for the next layer, we've also divided by 2, so 18 divided by 2 gives us the 9, 60 divided by 2 gives us 30, and I can do it one more time by dividing 9 and 3, and 30 and 3 to give us 3 and 9. We have to stop once we notice that we can no longer divide these numbers here by the same number. So what we're going to do is we are going to look for that GCF by multiplying all of the numbers on the left-hand side together. So this means that we've got 2, 2, and 3 together, and that gives me a GCF of 12. On the other hand, I'm going to take a look at my LCM by multiplying all of the numbers along the left and the bottom together. So we can see here that 2, 2, 3, 3, and 10 now all multiply together to give me my LCM of 360. Let's work on an example together here. So starting off with 32 and 80, I'm going to go ahead and divide them both by 2. So 32 and 2 or 32 divided by 2 rather, gives me 16. 80 divided by 2 gives me 40. I'm going to move on to my next layer, and I can divide both by 2. 16 divided by 2 gives me an 8. 40 divided by 2 gives me 20. So you still might have to use your calculator here if you're not very quick at dividing or multiplying numbers together, but that's perfectly fine. I'm going to now divide them both by 4. So 8 divided by 4 gives me a 2, and 20 divided by 4 gives me 5. I have to stop at this step because I can no longer divide both of these numbers by the same number. So I'm going to look at the left-hand side here. I notice that my numbers on the left are 2, 2, and 4, which means that my GCF is simply those numbers multiplied together. So in this case, my GCF is equal to 2 times 2 times 4, which is the same thing as 16. I'm going to do the same thing now with my LCM, except I'm also going to include my bottom numbers. So when you multiply those numbers together, I get 2 times 2 times 4 times 2 times 5, and that gives me a grand total. I've got 10 here times 8, so 10 times 8 is 80, times 2 gives me 160. For the next two examples, you guys can pause the video here, try it out, and then unpause to check your work. So we can see that one of the main benefits of using the cake method is that we don't need to worry about using factor lists or multiple lists in order to find the GCF and the LCM. What this does is it gives us a very streamlined way of figuring out what that GCF and LCM are at the exact same time. One way that we can up the complexity of this type of problem is by adding a third number. So the main thing to keep in mind is that if we reach a layer where we can only divide two numbers with the same outside number, we have to bring the third number down into the next layer and continue as usual. But once we do that, we need to make sure that we stop at that point to find the GCF. So the GCF stops here. So what that's going to look like in our example, we'll see that 12, 18, and 24 are all divided by 3. 12 divided by 3 gives me 4, 18 divided by 3 gives me 6, and 24 divided by 3 gives me 8. In my next layer, I'm going to divide all three numbers by 2, which gives me 2, 3, and 4. We'll notice that we can no longer multiply, or rather divide, all three numbers by the same number. So I have to stop my GCF here. So that means that my GCF has to be 3 times 2. So 3 times 2 gives me 6. What I have to keep in mind is that I can divide two of them by the same number. So I'm going to divide the 2 and the 4 by a 2. So 2 divided by 2 gives me 1, and 4 divided by 2 gives me 2. The last thing I need to do is note that I'm bringing this 3 down and it remains unchanged. I'm going to examine all three numbers one more time, and I see that I can no longer divide all 3 or even 2 of them by the same number, so I am complete, or I have completed this question. So looking at the LCM, I'm going to multiply everything here on the left-hand side along with the bottom, and this will give me an LCM of 72 in this case. Let's look at an example of 18, 45, and 72. I'm going to divide all three numbers by 3. So I've got 6, 15, and 24. I notice that I can divide it one more time by 3. So I get 2, 5, and 8. We see here that I can't divide all three numbers by the same number anymore. So I have to stop here and look at my GCF. So my GCF in this case ends up being 3 times 3, which is equal to 9. So that's going to be my GCF. You can see here that I can divide two of these by the same number. I can divide 2 and 8 by 2. So I'm going to go ahead and do that. And I'm going to bring this 5 down. I can't divide all 3 or 2 of them by the same number anymore. So my work here is complete. I'm going to take all of the numbers here on the left hand side. Oops, let me redo that. All these numbers on the left and the ones on the bottom, and I'm going to multiply those together to give me my LCM. So my LCM is 3 times 3 times 2 times 1 times 5 times 4. Let's see what I end up with. I've got 20 times 2, which gives me 40, and I get 40 times 9, which gives me 360. So once again, make sure that once you cannot divide all three numbers by the same number, you have to stop, multiply the numbers on the left together to find the GCF before continuing. In this last portion of AN1, we're going to talk about the idea of perfect squares and cubes. In previous math courses, you might understand that a perfect square means that we're multiplying two numbers together, or two of the same number together, to give us a perfect square, such as 4 times 4, giving us 16. In this case, 16 is what we would call our perfect square, because we have two of the same numbers multiplying together to give us 16. Now we can actually use prime factorization to prove that a number is either a perfect square, perfect cube, both, or neither. Now it's a little bit more complex than having just two of the same number once we use prime factorization, but really it comes down to the idea of having either two equal groups or three equal groups. So when we look at a perfect square, we are going to have two equal groups of the same factors, which will eventually end up in us having two of the same numbers. And then on the other hand, a perfect cube will mean that we are going to be looking for three equal groups of the same factors. So the way that we're going to go about doing this is using a factor tree. So we're going to prime factorize the number 64 here using a prime factor tree. And we notice that we end up having 6 factors of 2. So 2 times 2 times 2 times 2 times 2. From here, we can claim that it's a perfect square because we can clump 64 into two groups of the same factors. So I have a group of 3 2s and then a second group of 3 2s. So inside each of these groups, when we multiply the factors together, it gives us 8 times 8. So we notice that goes back to those two of the same numbers, two of those same factors, multiply to give us 64, meaning that it's a perfect square. I can do the same thing with proving that it's a perfect cube because instead of splitting this up into two equal groups, I'm going to split them up into three equal groups. So I'll have a group of 2 2s, another group of 2 2s, and then a third group of 2 2s. So when I multiply the factors inside each of these groupings together, it gives me 4 times 4 times 4, and it gives me 3 of those equal factors. That proves that this is going to be a perfect cube. So let's look at a few different examples together. 144, let's go ahead and prime factorize this. I'm going to go 2 and 72, 8 and 9, 4 and 2, 2 and 2, and it gives me a 3 and a 3. So you can see that 144 is the same thing as we've got 1, 2, 3, 4 of those 2s, and then I've got a 3 and a 3. So from here, we're going to split this up into two equal groups if we can. I'm going to put 2 2s plus a 3 inside each group. One common misconception that I get from students is that we need the exact same numbers, as in we can only have 2s inside of one and only 3s inside the other. Well, we want to think of this as having the exact same thing. So if I have 2 Kit Kats and a Hershey's bar inside of one bag, I also want 2 Kit Kats and a Hershey's bar inside my second bag. So we want to avoid doing something like this. So we've used up all our factors, which means that if we were to multiply everything that's on the inside of each group here, we would get 2 times 2 times 3, which gives us 12. And then we have 12 in my other grouping as well. So since I have 2 equal groups, then that means that we have a perfect square. So sometimes we're going to end up with a number that happens to be both a perfect square and a perfect cube. 729 is going to end up being one of them. So in order to prove this, let's go and prime factorize 729. So I can divide this by 9 and it gives me 81. I'll have 3 and 27. Continue on with the 9 here. So that's all done. Moving down to the 27, I've got 3 and 9, and I've got 3 and 3. This means that my prime factorization of 729 is comprised of 6 factors of 3. So for the first portion, trying to prove that this is a perfect square means that I would be able to divide this into 2 equal groups, which I absolutely can, which means that I've got 27 times 27. So I've got 2 equal groups of factors. So 2 equal groups of factors, therefore it's a perfect square. What I can also do with the 729 is actually split this up into 3 equal groups. So I'm going to do the same thing except with 3 groups, and you'll note that I have 2 3s in each group now, which means that I've got 9 times 9 times 9, and I've got 3 equal groups of factors. Therefore, it's a perfect cube. So hopefully you found this video informative and helpful. If you have any questions, feel free to leave a comment down below. There are definitely many other ways to look at things like GCFs and LCMs, but this is just my preferred way of teaching this to you guys. I hope you all enjoyed this video. Thanks again for watching, and I'll see you in the next one.